So today we have Digvijay Varier to tell us about Anomaly Mediated Supersymmetry Breaking. And he's a student at Berkeley.
Thanks. So I'll be talking about AMSB applied to SUN and SPN QCD-like gauge theories, which builds on work done by Marcus and Hitoshi in late 1990s, and then Hitoshi started this AMSB program to apply this to various gauge theories in like 2021. And then we have a paper that talks about this applied to SUN, QCD, and then later a paper that talks about the SUN conformal window specifically, and then we are almost done with a paper that talks about stuff on the SPN side of things. And that will be the content of the talk today. So we'll start with why it's difficult to study strongly coupled gauge theories, and that we have these properties of confinement and chiral symmetry breaking, which we know from experiment is true, but we don't have a first principles derivation for it. So we will introduce supersymmetry, talk about why it's useful to have SUSY, and then break supersymmetry by AMSB. And in QCD-like gauge theories, which has matter in the fundamental representation, we will look at the infrared phases for SUN and SPN and how they collapse to chiral symmetry breaking when AMSB is applied. We will be using Seiberg duality for our significant part of our analysis, and we will be deriving these chiral symmetry vacua and the softly SUSY broken limit, starting with the SUSY phases of ADS, quantum modified, constrained, s-confining phase, free magnetic phase, and conformal window. For these SUN, SPN, and SON theories with fermionic matter, we know that they are strongly coupled, so the IR dynamics are very much non-perturbative, and it's difficult to analytically derive chiral symmetry breaking in presence of massless fermions if you are in a non-SUSY theory. But if you are having supersymmetry in your theory, then it becomes relatively easier to predict like confinement, Coulomb phase, or IR fixed point like behavior. So our objective is to analytically prove quark confinement into hadrons, chiral symmetry breaking, and light NGBs in QCD-like theories. And the method we use is start with SUSY theories, do a controlled deformation using AMSB, and that gives us enhanced calculability, and we obtain exact results in the non-perturbative regime, provided SUSY breaking is small. At this point, that's all we have been able to get to. And SUSY is treated purely as a theoretical tool for our analysis, and it's not necessarily required to be a part of reality. So some quick review on stuff that most of you already know. Massless QCD has this Lagrangian, and these are some mass terms here for the left and right-handed quarks. And in the massless limit, and assuming only 3 light quark flavors up, down, and strange, we have this SU3 left cross SU3 right global symmetry, which is called chiral symmetry, which has independent SU3 rotations of the left and right-handed quark fields. And even when these light quarks have non-vanishing masses, as long as they are small, much smaller than this lambda QCD scale, this is a good approximate symmetry. But from experiment, we know that this is spontaneously broken into an SU3 vector subgroup. And the conjecture is that non-perturbative QCD dynamics will yield a chiral condensate that does not vanish, and that's a quark bilinear. And that is what causes this symmetry breaking. And then we use a chiral Lagrangian to predict quark mass ratios and meson masses like this, which you would have seen before. And this symmetry breaking predicts the 8 light pseudoscalar mesons as the pseudo-number Goldstone bosons, and in particular the pions being light is crucial for mediating the strong force far enough to bind nuclei together. So we know that this happens, but we don't have an analytical derivation for it. And lattice QCD is expected to get there at some point, but before that happens, our proposal is to use a special kind of SUSY breaking called AMSB, which we will discuss in the next slide, and to show the spontaneous chiral symmetry breaking. But first we have supersymmetry, and then we break supersymmetry. So in supersymmetry, there is this general renormalizable Lagrangian that we can write down for a non-abelian theory. And this thing here is called the Taylor potential. This thing here is the field strength term, and this thing is the superpotential, which has the interactions. This one, Taylor potential, gives the kinetic terms. And this thing in round bracket here is the holomorphic gauge coupling, which can be treated as a parallel background superfield, and it receives only one loop and non-perturbative corrections. The superpotential does not get renormalized due to a property called holomorphy, and that's called the non-renormalization theorem. And all the couplings run purely due to wave function renormalization. And these Lagrangians have moduli spaces, which are manifolds of inequivalent vacua parameterized by vacuum expectation value. We will use a lot of Seiberg duality. So for SUN, there are dual gauge theories that describe the same IR physics. One is called the electric theory with an SUNC gauge group. NC is the number of colors. And in the talk, we will use NC and N interchangeably, and NF and F interchangeably. NF is the number of flavors. So in a SUNC gauge theory with NF flavors of quarks, we have that called as an electric theory. And then the magnetic theory has a different gauge group, but the same global symmetry. And we have NF flavors of dual quarks and an independent scalar dual meso field. So this is the matter content. This is the electric theory here. This is the magnetic theory. This is the gauge group. This is the global flavor symmetry. We have baryon number because there are baryons in an SUN theory. And U1R symmetries because of n equal to 1 supersymmetry. So why are we looking at SUSY gauge theories? Because all these things that we talked about, like non-renormalization theorem, extra U1R symmetry that imposes more constraints, all these give us more theoretical control, and we also know that IR degrees of freedom in SUSY theories are gauge invariant holomorphic functions of the UV fields, like meson and baryon superfields, and these degrees of freedom are fixed by global symmetries and Truft anomaly matching. So we can basically write down the IR superpotential by imposing all these constraints. And we also have Seiberg dualities whenever the electric theory becomes strongly coupled. So this is like a commuting diagram that we have, that you have the SUSY UV with asymptotically free quark and vector superfields, and you have the non-SUSY UV with asymptotically free quarks and gluons, and we can connect between them by giving the superpartners masses, large masses, so that they get integrated out. And then we have the SUSY IR, which has composite meson and baryon superfields, and the SUSY IR has been analyzed in much detail by Seiberg, Intelligator, Pulier in the 1990s and others as well. And this is better known as Seibergology, and there are some very good reviews on this by Intelligator and Seiberg, and also in John's book. But what we don't have is an arrow connecting here all the way, because we don't know how SUSY breaking enters the non-SUSY IR EFT. So our attempt would be to use AMSB to make at least this connection partially. So anomaly mediated SUSY breaking is a kind of gravity mediation which has a property of sequestering, which is that the SUSY breaking sector and our visible gauge theory has no direct interaction, but everything happens via supergravity. In the SUSY breaking sector, there is this F term for some matter parallel superfield that breaks SUSY. That mechanism is not important for the results of this talk. But what happens is that induces a gravitino mass in supergravity, and then that shows up as a parameter that we call M in the visible gauge theory, and all SUSY breaking effects are encapsulated in N. And this has been described first in like Lisa Randall and Raman Sundaram's work in 1999, and then also in Marcus and Nima's work later. And also in this paper...
the order is wrong.
Sorry?
98 is before 99.
True.
Their preprint came out like 2 weeks before ours or something, or 1 week.
I see.
Doesn't matter.
And then in Marcus's paper, there was also this gauged U1R effects that were included. So far we have not included that, but using that in conjunction with AMSB can also be a good idea, and we do plan to look at it in the future. But right now we have used purely AMSB. So the way this parameter M shows up is determined by the coupling of this wild compensator, which is a non-dynamical parallel superfield spurion. and its coupling is purely constrained by supervile invariance. And it attaches to all the terms in the Lagrangian that are not already superconformally invariant, which is why it's said to compensate for that. And it can be removed by rescaling the fields if the terms are already conformal. So it only couples to non-marginal terms at the end of the day. So if you have a scalar potential and a superpotential, this is how the Weil compensator will couple to them. And it also couples to these fundamental scales like lambda. So it will show up in loop effects. And this has since this is only constrained by supervile invariance, it has a universal coupling at all energy scales, which is a property called UV insensitivity. And by coupling to the Weil compensator, we have coupled our visible gauge theory to conformal supergravity. And then when this compensator is given a wave, the F term of the compensator is this parameter M, which is the gravitational mass. And that is what encapsulates the SUSY breaking effects in the visible sector. And this is called Anomaly Mediated Supersymmetry Breaking because it's the violation of conformal invariance in the SUSY theory that tells us how the compensator will couple, and that is what determines how the M shows up. Okay. So at tree level, the AMSB contribution is given by this. It depends on the superpotential. So if the superpotential is 0, there will be no tree level AMSB effects. And also this result assumes a canonical scalar potential. If the scalar potential is not canonical, there is a more general result which we will introduce later in the talk. And at loop level, we have scalar mass squared coming from two loop scalar mass squared coming from AMSB effects. That's given by this formula. For example, the squarks will get this mass from AMSB. And then gatinos also get a mass given by this. These depend on the NSVZ beta function. And there are also A terms, but we don't use that in this talk. So we'll mostly be using this result and this result in all of our analysis. So with AMSB, we keep this parameter M non-zero, but much smaller than the scale lambda of the theory. And that means that we are in the softly SUSY broken limit, and at that limit we can derive chiral symmetry breaking vacua. And what happens when M is at order lambda, whether there's a phase transition or not, is an open question at this point. But some of the results that we get would seem to indicate that probably what we get is already resembling non-SUSY IR a lot. So there's likely no phase transition, but that's a conjecture at this point. But we will talk about that more. Okay. So on the UV side of things, AMSB can be used to make the complete connection to the completely SUSY broken theory. For example, if we have SUN gauge theory with F quarks in the fundamental and F anti-quarks in the anti-fundamental, this theory is asymptotically free for F less than 3n. And with that number of flavors, and in an electric theory where we have asymptotic freedom, so the superpotential is 0, so there will be no tree level AMSB effects. And the loop effects will give the mass squared for the squarks and a gaugino mass, and both of these are positive if F is less than 3n. So that means these can be integrated out if we take M to infinity, that is we break SUSY completely. And then we collapse to asymptotically free QCD-like non-SUSY theory. And this feature that the superpartners get positive masses and that the scalar potential will only depend on these mass terms, so M squared Q, Q twiddle, and M gamma, M lambda bar kind of terms. So the scalar potential will have a rising behavior with a minimum at the origin for any theory with asymptotic freedom as long as we are in the UV. And this will become important in a couple of slides.
Sorry, is there a square missing?
Square?
Square or?
Oh yeah, this one should not be a square, that's a typo. But yeah, no square here, but this square should. Okay. So this is an executive summary of what we got for SU and QCD in that paper. So this left-hand side is the SUSY version of the theory, which was analyzed by Seiberg. And we have many exotic phases here, 6 of them. depending on how the number of flavors compares to the number of colors. And none of these resemble chiral symmetry broken phase that we know from QCD. But when we apply AMSB to this, and in the softly SUSY broken limit we analyze the theory, we see that all of these collapse to chiral symmetry breaking minima, although we get global minima conclusively in 2 cases. In some other cases we get baryonic runaways, by which we mean that there are runaways of the potential to order lambda field values, not negative infinity. And when we are at order lambda, we can't use perturbation theory. So there's an incalculable global minimum, but what we can analytically calculate is a chiral symmetry broken local minimum in these 2 cases. And here we lose control of the Kähler potential completely because of baryons, and we cannot identify any minima for the quantum modified constraint. So this is the SUN story. We will go into each of these cases in more detail. But the fact that we don't get global minima for all these cases is not the best thing, but which is why we use SPN. But before that, a note on baryonic runaways. So this happens when we have to use the magnetic description of the theory to describe the IR, and the dual squarks of the baryons get webs. And in some of these cases, we see that far from the origin of the moduli space, the SUSY plus AMSB scalar potential becomes increasingly negative as the webs are made larger. There could be a local minimum close to the origin, but we are talking about the behavior far away. And it goes to large negative values, but that doesn't imply a runaway to negative infinity, because the scalar potential that we calculate is trustworthy only in the weakly coupled regime, where the mesonic or baryonic webs are small compared to the scale lambda. So we trust our theory here, or trust our calculation here. The theory becomes strongly coupled at order lambda, and at that order, the electric theory is also strongly coupled. So we cannot do any perturbative calculations there. But as we go much larger than the order lambda, we are in the UV, where the electric theory is weakly coupled, and that is an asymptotically-free theory for all our considerations. So there we know that from a couple of slides earlier, this potential will rise up again because of positive superpartner masses. So around this order lambda, we have an incalculable global minimum because we don't have control on higher order Kähler potential terms there. But
all you know is that the baryon number is spontaneously broken. Do you know that for sure? Because there's no minimum where there's no minimum near the origin that preserves baryon number.
That is true. Yes. When we look at the s-confining case, we will see that there is a baryon number. There is a baryon number conserving minimum close to the origin, and the baryon number breaking minimum is at order lambda.
Are there cases where you know that baryon number is broken in the AMSB thing, even if you can't calculate the properties of the vacuum, or what?
We don't know whether, so I don't think we know of a case where baryon number is broken at order lambda, but in the s-confining case, when we have baryon number breaking webs, we get a local minimum here. Sorry, I might have missed it. So this one, when the baryons have 0 webs, so that does not break baryon number. Yeah, so when we don't break baryon number, we get a local minimum from the s-confining case here. And when we break baryon number by giving the baryons a non-zero web, we are having a runaway to order lambda field values.
Okay.
But whether there is a spontaneous breaking that happens there is something we have not investigated.
Okay.
Yeah. Okay, so we consider SPN as a theoretical exercise because that helps us to get definite results, that is global minima in the softly SUSY broken limit in cases where SUN could not give us that. And this SPN is the gauge group, is the group that has a 2n dimensional fundamental representation. So in some places they call it SP2n, but yeah, that's what we mean by SPN. It's a subgroup of SU2. So SUN have these baryonic runaways. SPN does not have these baryonic runaways because there are no baryons in the theory. That is because we don't have a totally antisymmetric invariant tensor of more than 2 indices. So we cannot define baryons. There are some cases where the dual squarks in the magnetic description get tachyonic webs, or tachyonic tachyonic dual squarks, but they also don't produce any runaways because we will show that this supersymmetric contribution to the scalar potential will be a positive quartic, which will stabilize the runaway. And other than that, it is very similar to SUN in that it is asymptotically free for f less than 3n plus 1, and it has 2f quark superfields in the 2n dimensional fundamental representation. So we will discuss the phases for SPN because that's neater, and whenever SUN is very different from the SPN results, we will also draw comparisons to SUN. So this is a summary of what we are doing in this paper. So this, as you can see in the SUSY side of things, the phases are exactly same as what we had for SUN. And then AMSB gives us global chiral symmetry breaking minima throughout for SPN. The global symmetry on the SUSY side is SU2F instead of SUF left cross SUF right. So that's the global symmetry. There's also U1R symmetry in the SUSY theory. We have F flavors of these quark superfields. We have an invariant tensor J for the SPN group. We can form gauge invariant mesons by contracting these quark superfields with the J tensor. The classical moduli space of the theory for degenerate SUSY vacua is given by the D-flat constraints applied to the generic quark webs. And we can use either the quark webs or the antisymmetric meson webs to label various points in this moduli space, depending on how the number of flavors compared to the number of colors. So this quark web we can write as this 2n cross 2f matrix, and this is the D-flat web. After applying appropriate gauge and flavor rotations, we can bring it to this diagonal form. So this is a direct product with a two-dimensional identity matrix, so you can call this, this is diagonal, this is block diagonal, and this is antisymmetric, as you can see. So this is what we will mean by most generic webs when we consider various cases going forward. Okay, starting with the ADS space for f less than n plus 1, the SPN and SUN results are exactly the same. So we'll just discuss the SPN one. This is the SUSY superpotential for the theory given by Intrigator and Puglio. All superpotentials in the SUSY side of SPN will be from that paper. And this has M appearing in the denominator, so the meson web is pushed into the weakly coupled regime. And there the scalar potential is canonical in the quark superfields. So we will parameterize everything in terms of quark webs. We'll minimize along a D-flat direction. By that, we can take these phi's to be different from each other along the diagonal, but then if we apply like arithmetic geometric mean inequality to the scalar potential, it will be minimized for all the webs being equal to each other. And this is the value of the web at the minimum, which is much larger than lambda square, so it's consistent with the fact that we are doing the calculation in the weakly coupled regime. That's because m is much smaller than lambda in all our considerations, which means this factor is much larger than 1. So with this superpotential in the SUSY theory, if we just wrote the SUSY scalar potential, it would not have any vacuum. It will be a runaway theory. And with AMSB, we have a chiral symmetry breaking vacua in the vacuum in the weakly coupled regime, and that breaks SU2F flavor symmetry to SPF. One flavor up, or not really, f equal to n plus 1. We have the theory that has a zero superpotential but a quantum constraint, which is a constraint on the Pfaffian of this meson web, which sets it to an order lambda value, as you can see here. And when m is of order lambda, our theory loses control on the higher order scalar terms. We need this to be much smaller than lambdas, as we had in the ADS case, for trusting the AMSB calculation. So what we do here is we do a nonlinear analysis. We start with the point of enhanced symmetry where all the meson webs along the diagonal are equal to each other and satisfies this constraint. That's called the meson point. And then we fluctuate around that by parameterizing fluctuations through this pion superfield, which is diagonal and traceless. So we have this ansatz for the meson web. And we try to write down all flavor invariants that can appear in the Kähler potential. These are 3 examples. And up to quadratic order in pi, we see that they all are proportional to this factor. So they might have some coefficient in front. So when we add up these flavor invariant contributions, this coefficient in front will add up to some constant c, but that needs to be positive at the end of the day to have a physical kinetic term for the pi. So we know that Kähler potential up to quadratic order in pi looks something like this. So we can plug that into this generalized tree-level AMSB formula for the scalar potential. And here G star is the inverse scalar metric, K is the Kähler potential, W is the superpotential, M is the SUSY breaking parameter. And that gives us this AMSB contribution, SUSY plus AMSB contribution to this. There's no tree level, The superpotential here was 0, so any term that depends only on the superpotential will have a 0 contribution. So this is the result that we get in terms of the pi fields. Here eta is 1, because you can check here, this was half. So we set that eta over 2 so that we can show that this term here is 0. So the imaginary part of the pion superfield gets a vanishing mass, so that can be identified as massless chiral symmetry breaking number Goldstone bosons. And the real part of the pion degrees of freedom, they give positive mass, so no runaway from that direction. So this is a stable theory, and it's a chiral symmetry breaking minimum in the physically allowed moduli space. This is something we cannot do in SUN, by the way, because we cannot make this particular argument. So here we made an answers for the mesons. We didn't have to consider any baryons. But we, in SUN, doing this for the baryons and turns out to be difficult. Like looking at both the meson and baryon fluctuations, and there we cannot identify any. Next we have f equal to n plus 2, which in the SUSY theory is a theory that has confinement without chiral symmetry breaking. That's called s-confining theories. And the superpotential is this for SPN. And the Kähler potential is taken to be canonical in M. There is no Yukawa term in the superpotential, so no two-loop AMSB effects, only tree-level effects. We look along this direction. We get this minimum for the scalar potential at this value of the wave, which is smaller than lambda because M is much smaller than 1. We have set lambda to 1 in our calculations. And kappa here is an order 1 coupling. Graphically, this looks something like this. This is a chiral symmetry breaking minimum, where your SP2F is broken, SU2F is broken to SPF. And any higher order Kähler terms, which do exist, but they are all at higher order contributions in the M, so we can neglect those. And this is our global minimum. On the SUN side of things, there is a Yukawa coupling with the baryons involved. And we can give the baryons waves that will be column matrices, and using appropriate flavor rotations, we can put all the make all entries 0 except 1. And if the baryon wave is non-zero, that will be a baryon number breaking direction. The SUSY plus tree level AMSB contribution turns out to be becoming increasingly negative as the wave for the meson is made larger. So that would be a runaway to order lambda field values, like seen in this green curve here. But close to the origin, if you look at the loop level AMSB effects, that goes at v square. So for n greater than 2, v to the n is suppressed compared to v squared if v is small. So close to the origin, we have a stabilization effect, but far from the origin, we have a runaway to order lambda field values. There's another direction where the baryon has a 0 wave, that's the baryon number conserving direction. That's this red one here. That has a tree level and loop level contribution at the same order, and that gives us a chiral symmetry breaking minimum, but that's a local minimum, because this runaway to order lambda field values will give us a global incalculable minimum. So for this phase in SUN, we get a local chiral symmetry breaking minimum analytically.
But do you really trust so the green curve is the one illustrating the runaway? Do you really trust the region where it's turning over, or is that already the region where you're out of control?
That's already out of control.
So you don't even know that there's a runaway.
Right. So we know that much larger than lambda, we will be switching to the electric theory, and there the potential is expected to rise.
Yeah, but you don't know that there's a minimum in between, or you do.
If it's like going down here and rising up there.
But you said you couldn't trust it. That's why I'm asking. Can you trust the part of that curve that's turning over and going down? Or
Oh
is
yeah,
that-
like going down is trusted. But
It's
how much
trustworthy.
it goes down and turns over, that is not.
Okay, so that is under control.
Yeah,
That part of-
this part is, yes.
Okay. So this is only for illustration. I mean, there it's called 0.8 times lambda, but that's, it's under control, right? It's under control of some control parameter. It's not
Yeah.
0.8.
Yeah,
Okay.
yeah. Yeah, this is just plugging in some numbers.
Mhm.
Yeah, this is for n equal to n.
So
Yeah.
if you made m 0.01 times lambda, then the bump in the green curve moves to the left, so it's more under control. Is that what
Sorry?
you're saying?
Yeah.
The control parameter is m, so if you
Mhm.
took m smaller, then it would move to the left?
Yeah.
Okay.
Yeah. Yeah, you can see that kind of, it's proportional to it. So.
That's the height of the potential, but the minimum of the potential, the position of the minimum,
Position
also
of the
moves to the
minimum.
left? It's
Yeah.
also,
Yeah.
it also moves to the left,
Yeah.
okay, yeah. Just making sure, thanks.
Okay, so for higher number of flavors, we need to go to the magnetic dual because the electric theory turns out to be strongly coupled. And this was described by Intelligator and Pullier. Here we have a magnetic description of IR physics with a different gauge group, with F minus N minus 2, which we will call N twiddle, and the same global symmetry. We have F flavors of dual quarks, which we will call small q, and an antisymmetric gauge singlet M, which is not a meson of these q's. This is a separate dual meson. And this is the superpotential of the theory. Lambda is the Yukawa coupling. This is a marginal superpotential, so this will not lead to any tree level AMSB effects, but it will give loop level AMSB effects. In the SUN theory, this superpotential looks similar, but one of the q's is replaced by the anti-quark, anti-dual quark. And this is a UV-IR duality between the electric and magnetic theory, which is also a Higgs confining duality, and also when the electric theory becomes stronger, the magnetic theory gets weakly coupled and vice versa. So for n plus 3 to 1.5 n plus 1 number of flavors, we have a free magnetic phase, non-abelian, where the theory becomes IR free, the magnetic theory becomes IR free. And we have a trivial fixed point where the couplings go to 0 and the beta functions also go to 0. And the coupled beta functions close to this fixed point allow us to write the couplings in terms of each other at one loop. And that gives us this trajectory. This is a straight line trajectory along which the couplings should flow to the fixed point in coupling space. And the renormalization group equations, that is the anomalous dimensions and the NSVC beta function, are given by these in terms of the couplings and n twiddle and number of flavors. We can use the two-loop AMSB mass formula to show that the scalar mass squared for m and q are positive as long as f is less than or equal to 1.43 n plus 1. So for most of this window, that is true. But at the very upper edge, from 1.43 to 1.5 n plus 1, mq squared is negative. So we'll show that that does not lead to a runaway. This is an example of the RG flow. These are in terms of the 't Hooft couplings, so these are proportional to coupling squared. This is the trivial fixed point here. This flow to the fixed point becomes the straight line as we predicted in the previous slide. This is for f approximately 1.43 n plus 1, so for f equal to 330 and n equal to 230. And this is the point where we expect mq squared to switch from positive to negative sign. So at around this number of flavors, it should be roughly 0. And this red line is the set of points where mq squared is 0 on this plot. And we see that that converges with the straight line trajectory here. And it's also to the right of the green line, and everything to the right of the green line is denoting m square greater than 0. So this is a pictorial representation of what we got as results on the previous slide.
So
Yes.
if I'm understanding, that mass switches sign when you cross the red line.
No, this is...
And q squared, that red line is
Oh
marked
yeah,
q
yeah,
squared
yeah,
equals 0?
yes. So,
So which...
everything to the right of a line is positive, everything to the left of the line is negative. And for the
So
choice of... Sorry.
the out of control region is between the green and the red.
The out of...
Or to the left of the red line is out of control.
Right?
Because there's a runaway? Because the mass
Oh,
squared
we
is
will
negative?
show that there is no runaway in the
Okay.
next slide. So for SPN there is no runaway. So we will look at this range of number of flavors where there is this tachyonic dual squark. So we will give this dual squark a wave, a D-flat wave, and we will also, for generality, give the mesons a wave, and we will show that that is what is to be done to have a consistent result, because the dual squarks, this is the kind of wave that we have for the two of them, and we need to give the mesons a wave also, because once we write the scalar potential down, we see that this does not have a minimum at phi m equal to 0, so we cannot integrate out the m. So we have to give the m also a non-zero wave. This pair of terms here is the SUSY potential. This one is the tree level AMSB contribution, and this one is the loop level AMSB contribution. And this is analytically hard to minimize if none of these waves are 0. So we do a numerical exploration for various choices of number of flavors, colors, and m parameters. Close to the fixed point, we can write the couplings at leading order by these expressions from the coupled beta functions. And these are the mass squareds coming from the AMSB 2-loop formula. We can plug these back into this potential, which would then give this potential in terms of NC twiddle, NF, parameter M, and phi m and phi q, which are our webs. And if we then do a contour plot in the phi m phi q space, we see a single minimum at non-zero finite values of phi m and phi q. And that's on the next slide, but before that, in the SUN side of things, we will not have this positive quartic term in phi q, because this comes from this superpotential being mqq, but in SUN it is mqq twiddle, so we won't get this positive quartic, and this positive quartic will be dominating at large field values for phi q, and that is what will stabilize the runaway due to the tachyonic master for phi q. But that doesn't happen in SUN. So in SUN we would have a runaway to order lambda field values whenever the dual squark gets a tachyonic value. So the contour plot is this. This is the minimum of the potential at non-zero values of phi m and phi q. So this will be a chiral symmetry breaking minimum where the symmetry is broken to SPN twiddle cross SP 2F minus 2N twiddle. This is a 3D plot of the potential, so we have a minimum there. And this is done for n equal to 14, f equal to 22. But this minimum that we get will end up being a local minimum, because the global minimum is shown to be from the pure Masonic branch. But we don't see a minimum here on this contour plot along the pure Masonic branch, because this scalar potential that we wrote didn't account for non-perturbative effects. So if we do a post-priori justification, we could integrate out the dual squarks first, then derive the minimum of the low energy super Young's-like theory, which takes into account gauging of condensation like non-perturbative dynamics, and then plug in that phi m wave back into the scalar potential to get an effective potential for phi q, and then try to minimize it, and we see that that has a minimum at phi q equal to 0. So post priori we know that it was consistent to integrate out the dual squarks. So that can give us a different direction along a pure Masonic branch. And then numerically comparing that minimum to the dual squark minimum, we see that that is the deeper minimum, which we will show on the next slide. So the global minimum comes from a pure Masonic branch. This is the Masonic branch. As long as we are less than 1.43n, this is the only branch in our theory. But if we are above 1.43n, then we have the dual squark and the pure Masonic branch competing, and numerically the Masonic branch is the deeper one. But for less than 1.43n, we can just integrate out all the dual squarks because they are positive mass squared. And the low energy EFT looks like this. This is an exact non-perturbative superpotential, which can be written from Gaugian condensation. We have a new confinement scale. The 3-level AMSB gives us a minimum, which is a color symmetry breaking minimum, and since this is the only branch in F less than 1.43n plus 1, this is the global color symmetry breaking minimum there. And numerically, we conjecture that this is also the global chiral symmetry breaking minimum for this small range here. And whenever the pure Masonic branch is the minimum, chiral symmetry breaking minimum, it breaks SU2F to SPF. For 1.5n to 3n, we have the conformal window. And I will discuss this for SUN. Firstly, because we have a paper on that. And secondly, because the SPN and SUN results are roughly the same in the conformal window. So here we have a non-trivial IR fixed point. So beta functions go to 0 when couplings are non-zero. Electric and magnetic descriptions give the same analytical fixed point. Since this is a conformal theory, the dimensions of chirals of primary operators can be written in terms of R charges. Our argument is that if the AMSB masses scale sufficiently slowly compared to mu as we go into the d pi r, then we'll say that the AMSB effects are relevant. And they will deflect the superconformal dynamics to chiral symmetry breaking in the d pi r. So the goal is to study mu dependence of the masses and also derive chiral symmetry breaking minima analytically. So we want to do this in a perturbative fashion. So we want either the magnetic coupling or the electric coupling to be small, which then constrains us to be at the upper or lower edges of the conformal window where we have Banks-Sachs fixed points. And then we can make conjectures about the intermediate conformal, bulk of the conformal window where both theories are strongly coupled. So at the edges, these graphs show that if we are at the upper edge of the conformal window where NF is close to 3 NC, there the electric gauge coupling is small, whereas it becomes larger as we go to the lower edge of the window. In the magnetic theory, both the gauge and Yukawa couplings are small at the lower edge of the window and they become larger as we go to the upper edge. So at the lower edge of the window, where epsilon parameterizes how close we are to the lower edge, so F is roughly 3/2 n, and we keep epsilon to be very small. We have these Tuft couplings, which are the original couplings squared with appropriate normalization. We can write the beta functions in terms of the Tuft couplings, and this coupled system can be solved. We have two eigenvalues. One is, and the trajectory with this larger eigenvalue will run to 0 faster, and then we'll have the resultant flow along the lesser eigenvalue trajectory. So this will also give us a straight line trajectory like we had for the free magnetic phase. And the coupling, the fixed point in terms of epsilon is given as 2 epsilon comma 7 epsilon, which you can get by setting these beta functions to 0. This is the trajectory along which the couplings flow to the fixed point. Delta x and delta y are the difference between the couplings and their fixed point values. And if we solve this by plugging back into the beta function, we see that these go as mu to the 21 epsilon squared, which is slower than mu squared if epsilon is sufficiently small, which can be translated into a limit on the number of flavors. So if f is less than 1.77 n, which means that we are well into the lower half of the conformer window, then this AMSB effects are conclusively shown to be relevant in the d pi r. So we trust this result as long as that number of flavors is the case. Okay, and this is the RG flow, again in Tuft coupling space. We can flow to the fixed point now from either above or below. If we flow from below, the two-loop AMSB mass formulas give us these results, which depend on delta y, and flowing from below, delta y will be negative. So mm square will be negative, mq square will be positive. So we expect that to give us a pure Masonic branch minimum. If we had flown from above, then mm square would be positive, mq square would be negative. And then from what we learned in the free magnetic phase, we can do a similar calculation, and we will see that if you are in the SPN theory, you get a local minimum from the mixed branch and a global minimum from the pure Masonic branch. But if we are in an SUN theory, there will be a runaway due to the tachyonic dual squarks. But we are free to choose initial conditions in a way to get a pure Masonic branch. So if we choose initial conditions such that we are flowing from below the fixed point, then we can always get a pure Masonic branch. And that's what we will analyze in the next slide. For SPN theory, we can flow from above or below. We'll always get a pure Masonic branch. Okay, so we can integrate out the dual squarks if we are flowing from below. And then we have this effective superpotential. The analysis is slightly different here in that the wave function renormalization is not logarithmic in the conformal theory because the anomalous dimensions are large. So these will show up in the Taylor potential, making it non-canonical. That means we have to use the generalized AMSB scalar potential formula and account for these z factors. So they show up like so. So this one is the two-loop AMSB contribution. This is the tree-level AMSB contribution. This whole thing here is the tree-level AMSB contribution, and then that one is this supersymmetric contribution to the scalar potential. We are also trying to analyze the theory close to the fixed point, but not exactly at the fixed point. So we want to write the anomalous dimensions as the fixed point values plus a deviation. And we know that the anomalous dimensions are linear in the 't Hooft couplings, and the 't Hooft couplings go as mu to the 21 epsilon square. So the anomalous dimension can be parametrized in this fashion, where alpha is 21 epsilon square. And then if we give the meson this generic web, we get a parasymmetry breaking minimum of this order, and this is not having any baryonic instability because mq square was positive. Going to the upper edge, again epsilon parameterizes how close we are to the upper edge. We have only one beta function because it's just the gauge coupling in the electric theory. We know that the electric theory is weakly coupled in the UV, so we must flow to the fixed point from below in coupling space because the coupling away from the fixed point is smaller. And near the fixed point we can write the coupling, solving the beta function that we have here. It will go as mu to the 3 epsilon square, which is again slower than mu square if f is greater than 1.65 n. So as long as we are well into the upper half of the conformal window, we have trustworthy results that AMSB effects are relevant. And mq square and the gaugino mass can be written down in terms of the difference between the coupling and its fixed point value. And since we are conclusively flowing from below here, both of these are positive. So both superpartners are having positive masses, which means as we flow to the minimum of the potential, which will be at the origin of the potential because superpotential is 0 in this theory, somewhere along the way, the masses of the superpartners will exceed the RGE scale mu, so we can integrate out the superpartners, and before we reach the minimum, the superconformal phase is destroyed, and we go to non-SUSY QCD, which is strongly coupled because the beta function changes in the non-SUSY theory. So then the low energy description at the minimum of the potential can be done not by using the electric theory, but by using a twice dual theory. So twice dual theory is taking a dual of the magnetic theory, which in the supersymmetric limit would just give you back the electric theory, because the SUSY equation of motion would set M, which is the dual meson, to QQ toodle, where Q is the dual quark superfield, and N is the meson superfield formed by the dual quark superfields. So if you are in supersymmetric theory, you will get N equal to 0 from the SUSY equation of motion, so it acts as a Lagrange multiplier, setting this to be the meson of the electric theory. But if you apply AMSB, M is no longer 0. So you can do an RG analysis identical to the magnetic one, because again you have this Yukawa-like term with a Yukawa coupling in front, which we will call Y instead of lambda. And we also have this Mn term. So if you try to integrate out the quarks, the low energy effective theory will have the super Yang-Mills-like term and an extra term, which will be like an N and M. Also, we know that twice dual theory and the electric theory describe the same physics in the IR. So if the electric theory told us this mq square is positive, then in the twice dual theory we should flow to the fixed point in a way that mq square is positive, which would then set mn square to be negative from the RG equations. So we integrate out the q's, give n and m full rank webs, and this ends up being the superpotential. And then we keep track of wave function renormalization factors, and at leading order we analyze the scalar potential. It turns out to be symmetric in M and N, so we can set their webs equal to each other, and then we find phi at the minimum, which ends up being this. So that is a stable chiral symmetry breaking minimum at the upper edge of the conformal. So we did the lower edge, upper edge. In the bulk of the conformal window, it's a conjecture that there is a chiral symmetry breaking minimum because we can't do perturbative calculations in the bulk. For higher number of flavors, the electric theory is free, which means that we cannot apply AMSB because AMSB is applied only to asymptotically free theories. If we try to apply AMSB, the superpartners will get negative masses, and that would be a true runaway behavior. So AMSB is not applied for this range of flavors, for SPN and SUN. That takes us to the summary. For SPN, we were able to show stable chiral symmetry breaking minima, breaking SU2F to SPF for all number of flavors up to 3n plus 1 with some conjectures in the middle, but the conjectures were based on numerical calculations. And this was in the small SUSY breaking limit, so this is a promising result as far as a controlled approximation to QCD-like theories is in question. Going case by case for the quantum modified constraint, we had a strongly coupled nature for the theory from the constraint, so we had to do a non-linear analysis around the meson point, and we showed a stable chiral symmetry breaking minimum for SPN because there were no baryons involved. For F, the greater than 1.43n in the free magnetic phase, we showed that there were tachyonic dual squarks, but the runaway was protected due to a positive quartic contribution from the SUSY scalar potential. And the SUN side, this doesn't happen, so there we get a runaway to order lambda field values. In the conformal window, we worked at the upper and lower edges around the Banks-Sachs fixed points, and we showed a chiral symmetry breaking minimum using the magnetic and twice dual descriptions. All of this was in m much smaller than lambda limit, but the real world limit is m much larger than lambda, so we would like to know if there is a phase transition at m of order lambda, but that is an open question at this point. The AMSB conjecture is that there exists some class of strongly coupled theories that are continuously connected to their AMSB counterparts, which means that they would have the same vacuum universality class. When and how this conjecture fails is an active area of research, but if it turns out that for anomaly mediated SUSY broken QCD and QCD, the universality class of the vacuum is the same, then this could turn out to be an analytic demonstration for chiral symmetry breaking in QCD. With that, I would like to end. Thank you for listening.
Questions?
Why is it called anomaly mediated instead of supergravity mediated? Or is it?
It's the super conformal anomaly mediated. So it's a super conformal anomaly that determines how the compensator couples, which determines how the SUSY breaking effects show up in the parameter M. So they just dropped the word super conformal and called it anomaly mediated SUSY breaking.
That's the word that was already used.
Can you go just back to the conclusion slide just now?
Yeah. Oh, that's the wrong direction. That's still the wrong direction.
There you go.
Good.
No? Okay.
Yeah.
So I'm just always confused about what is it that we're supposed to be learning here. So you say things like it's promising as a controlled approximation to QCD. So how would we? What does that mean? And how would you make good on that promise? What needs to be done?
So far in the small SUSY breaking limit, we are able to show a phase of the IR theory that resembles what we know in regular QCD, that is chiral symmetry breaking vacua. Except that the theory still has a fair amount of supersymmetry in it because we have only softly broken supersymmetry. So what we would need to do is to do calculations at m of order lambda and show that we still have the same results, which at the moment we don't know how to do because the tree level AMSB formula, for example, and the loop level AMSB formulas kind of assume that m is small compared to lambda. So there will be higher order contributions. And in many of the cases, we also made statements like the scalar potential contributes at order m that is larger than the tree level contribution, so we drop those extra terms, which we cannot drop if m is not small compared to lambda.
I completely understand the issue. The question is, now this has been going on for a number of years, and I keep hearing that all we need to do is think about the m of order lambda or m greater than lambda. Is anybody actually working on that? Are there any ideas for that?
So there are people trying to show that AMSB gives us phases in the softly SUSY broken limit that does not resemble regular QCD. For example, this one. For n equal to 1 and f equal to 3 SPN theory. Vai and Stolarski did this in 2022 for an SU5 GUT as well. And they try to show that in the softly SUSY broken limit, these theories give the confinement without chiral symmetry breaking, which is not what we would expect from a regular QCD theory that does not have supersymmetry. So their conclusion was that we probably need to add some deformation to this theory to make it look more familiar to what we expect from non-SUSY theories. And the thing that was common to both this n equal to 1, f equal to 3 theory and this is SU5 GUT was that they had classically conformal superpotentials, which means that the tree level contribution from AMSB was 0. So this is something people are trying to do. And then there was also this paper by...
But that's again for small m, right?
Yeah,
so
that is for
you
small
can
m.
find out that for small m it doesn't look anything like QCD.
Right.
I'm just saying that let me just put my cards on the table. I think there's no hope and no idea for any way of going to large m.
At this point, that is true. Yes.
Right.
Yeah.
But then why do this? I mean, why is this promising? In what sense is this promising?
And the fact
what are
that
we learning then?
You have shown chiral symmetry broken vacua for a non-SUSY theory, although that's not completely non-SUSY, but it's a theory that does not have supersymmetry and has an analytical demonstration of chiral symmetry breaking vacua, which resembles QCD.
Like the linear sigma model.
Sure.
Right. I mean, if I took the linear sigma model, if I took a scalar coupled to QCD, coupled to quarks, okay, that's my UV theory, so instead of making it supersymmetric, I'm putting in a scalar, and then there's a regime where the scalar gets a big VEV, okay, and Higgses everything, and I have some Higgses for QCD, then at low energies, I can find that I have the same chiral symmetry breaking as in QCD, and all I have to do is show that there's no phase transition as a function of these scalar masses when I make them large, so that I need to integrate out the scalar before all this stuff happens. So,
yeah, one
but
thing...
I don't think that, there's no reason to think that that teaches you anything about QCD.
Yeah, and there's also a proposal to use holomorphy arguments to say that there cannot be a phase transition. Again, there has been no paper on that, but that has been an idea that has been floating around.
So haven't we already seen that there are phase transitions?
In some cases, it seems like
Yeah, the conformal windows don't match, so
Conformal windows
of QCD and anomaly mediated SUSY QCD, they don't match, so there's a phase transition somewhere.
Why did I mean, we are able to show chiral symmetry break.
In the regime where QCD, non-supersymmetric, I think he's asking about the regime where QCD, non-supersymmetric QCD has a conformal window.
Mm-hmm.
In that regime, this anomaly-mediated SUSY breaking is not giving you a conformal window.
No.
So that's a case where we know there is a phase transition.
True.
So this proof that holomorphy gives you a phase transition somehow only works for certain numbers of flavors and certain theories.
That is true, but the conformal window of non-SUSY QCD, what is the range for that?
It's like
It's pretty
4
high.
NF to what is it, 16 halves NF, whatever.
4 NC?
4
NF
NC
equal to 4
to
NC.
16.
Yeah.
So it's beyond the-
here we went up
17
to
halves, whatever.
we went up to 3 NC here, right? In the SUSY.
Because they lose asymptotic freedom. In the
Yeah, so
SUSY.
we didn't go up to 4 NC, so we are not having a prediction from him.
But so, I mean, I got lost in all these things. So there's no case where we know there's a phase transition. In other words, you're able to either have uncontrolled vacua or you have a controlled vacua with the right thing in all cases,
Yeah.
even in the SUN case.
Wait,
Yes.
does an uncontrolled vacua mean there's phase transition?
I don't know if they don't have.
If one has a
control.
runaway and the other one
If,
doesn't,
if,
that's a
if,
phase
the,
transition.
if the global, the incalculable global minimum, even though it's incalculable, if it comes from the dual squark branch, then it has a symmetry breaking pattern that is not SUNF left cross SUNF right to SUN vector. So if the dual squark branch ends up being the global minimum in any case, that indicates a phase transition.
These counterexamples require phase transition.
Yes, but one thing that I notice is that they say it's classically conformal, so no tree-level contribution. But what they do there is when they write the wave function renormalization factor, they don't account for. Let me go back to wrong direction. So. What has been done in works so far is to write the tree level contribution with this 1, but not this anomalous dimension over 2. This is a contribution that comes from looking at the higher order terms in theta, where theta is the superspace coordinate, for the wave function renormalization factor. So this is important because in a classically conformal theory, this contribution that comes from the 1 will cancel with this. So I think that might have an effect, although I have not worked it out. So here we have used that contribution, which does play a role in our effect result. So maybe that if we include that, then those theories will also give consistent results, but I have not checked. But if it doesn't give a different result, then yeah, that indicates phase transition in theories that have those kind of classically conformal potentials.
But this is just the standard, I'm confused, because this gamma effect is just the standard effect that why you don't, like any like a Yukawa superpotential, right, is classically conformal invariant.
Mm-hmm.
But obviously we have anomalous dimensions from Yukawa terms, and so that's that term. I mean, that's just a completely
this was
standard
there
part
in
of
your,
AMSB.
this was there in your paper too.
Yeah,
from
yeah. So I'm
1998.
just asking, how could they leave it out?
Yeah, I don't know.
So you're saying the paper's just wrong? You're just saying it's wrong because they didn't actually use the correct AMSB formula? I'm just trying to understand what are you saying?
I should check that again, but as far as I recollect, this was not there in that paper. I can check it right now.
Oh.
Yeah, I can check it.
I mean, just the other thing is,
Yeah.
obviously there are many cases, a lot of these things, not everything, but a lot of these things were certainly studied in the late 90s, and, certainly some of us had a dream that there could be no phase transition, but it was immediately crushed by, lots of examples that weren't AMSB, but there are lots of other supersymmetry breaking examples where certainly you have baryon number, spontaneous baryon number violation, all kinds of things under beautiful theoretical control. So if there's some sort of no phase transition thing, somehow it's only true for anomaly mediation, right? Certainly not true for general SUSY breaking. So, okay. But is anybody actually working on it? Because I've been hearing these things for years, and everybody says it's promising. Is there anybody thinking about large M? What happens if we go to large M? Thinking about why there isn't a phase transition?
So one thing that Hitoshi has suggested is to use U1R gauge with AMSB and try to show that these dual squark incalculable global minima get lifted when you add the U1R gauge contribution, so that you always get Masonic.
That's still
but
wrong.
that's
That's
not
still
large
only
M.
true at
Yeah.
small m. That's
Yes.
still doing another thing at
So
small m.
yeah, so currently the
So you can keep
goal
doing
is to
more
get
things at small m.
everything at small m to look exactly like QCD. That's the I think the first step that we are thinking about. But yeah, at large m, I am not aware of anyone working at this point. Because if it would be someone, I think it would probably be Hitoshi or Chava or someone that either of them know. So I don't think that is happening at this point. Yeah, Hitoshi again likes to make this analogy, which is why I had this slide here. I don't know why this yellow came, but yeah, okay. To VEC crossover, where again we have this like continuous parameter 1 over KFA, where 1 over KF is the interparticle distance. And this is a smooth transition in that parameter that changes the phase like this in condensed matter theory. And from experiment we know that there is no phase transition at this unitarity limit, which is the intermediate stage. So if we compare this to m going from 0 to infinity, then it's an analogy to a proven condensed matter result that there is no phase transition. And again, like this is the analog to the SUSY version of the theory. This is the analog to softly SUSY broken theory, which has a lot of properties like superfluidity that completely is identical to the completely SUSY broken theory as an analog. Yeah, this is something Hitoshi likes to talk about. But again, no proof at m much larger. But yeah, we draw analogies. Things.
So in your case, SUSY helps you with some QCD stuff because you can do the duality and swap big component with small component.
Yeah. Not only duality, even like writing down the IR superpotential is a feature that is mainly thanks to holomorphy, which is only in SUSY theories.
Okay, let's thank the speaker again.